let us discuss about the realization of FIR filters. There are different types of realizations for FIR. The first type is called as direct form. The second type is linear phase FIR filter. Third is cascading, and fourth is lattice form. Now, we are aware that the system function of FIR takes a form something like this. We have the coefficients B0, B1, B2 till the very last term, and we have a series which is negative powers of Z. Now, the implementation of this can be thought of using direct form realization as shown. This primarily arises because from the system function we can obtain the difference equation in a very simple way. We are aware of the procedure for finding the difference equation. We have to change or replace h of z by y of z by x of z, which is equal to the quantity here. Then when we cross multiply the B0, B1, B2, all these terms, they are multiplied with y of z, and x of z is multiplied with 1. Cross multiplying and taking inverse z transform will give you the difference equation, which is y of n equals, okay, let us write the steps. Okay, we shall write the steps. So after this equation, next we obtain what is called as B0 plus B1 z inverse plus B2 z power of minus 2, the last term Bm z power of minus n. Okay, so this multiplication will give you what is x of z into all these terms. Later, after cross multiplying and taking the inverse z transform, so we are going to take the IZT after cross multiplying, we get the difference equation as y of n is equal to x of n times B0, or we can say B0 times x of n plus B1 times x of n minus 1 plus B2 times x of n minus 2, and so on. The final term we can say is Bm times x of n minus m. Okay. Now for this difference equation, it is possible to write a structure in direct form as shown below. Okay. So we have the input called as x of n. Passing it through a unit delay gives you the signal x of n minus 1. The subsequent delay produces x of n minus 2, and so on. The final delay element gives you x of n minus 1, n minus m. We have observed from the difference equation that the corresponding inputs are scaled by the coefficient B0. X of n is multiplied with B0. X of n minus 1 is scaled by B1. X of n minus 2 is scaled with B2, and this process continues. And we are going to make a sum of all these terms. So we have adder here. The product terms are combined here, and this sum is added with the product, which is B1, B2 times x of n minus 2. This continues to the very last, and combining all these values gives you the output called as y of n. So this is called as direct form realization. In the case of FIR, we do not have direct form 1, direct form 2 like we had for IAR. Here just we have a simple direct form realization. Let us take a numerical and let's understand the process. The question goes something like this. Realize an FIR filter with impulse response h of n given by h of n is equal to 1 by 2 to the power of n u of n minus u of n minus 4 using direct form 1 or simply direct form realization. Now let us note down what is given. Given is h of n is equal to 1 by 2 to the power of n, u of n minus u of n minus 4. The values may be computed taking the help of the expression. First point to be noted, what is u of n minus u of n minus 4? This is a sequence which exists from 0 to 3 and it carries a value which is equal to 1. The amplitude here is equal to 1 and it is present between n is equal to 0 till n is equal to 3. And this value is multiplied with the amplitude which is 1 by 2 to the power of n. Therefore, when the value of n is 0, 1 by 2 to the power of 0 becomes 1. Therefore, the magnitude at n is equal to 0 is equal to 1. When you consider n value as 1, the magnitude becomes 1 by 2. So 1 by 2 into 1 is 1 by 2. Next, 1 by 2 square is 1 by 4 into 1 makes it 1 by 4. Next, for n is equal to 3, it is 1 by 2 cube, which is 1 by 8. Multiplied with 1, it is 1 by 8. Hence, we have obtained the sequence by simply solving the given expression. Therefore, this sequence can be expressed by taking the help of impulses as follows. So we have delta of n, the first term, because the amplitude is 1 and it is present at n is equal to 0. Next, a shifted impulse, delta of n minus 1 depicts this point. Its magnitude is 1 by 2, so we scale it by 1 by 2. Similarly, 1 by 4 at n is equal to 2 and 1 by 8 at n is equal to 3. Next, taking the transform on both sides, we obtain h of z equals 1 plus 1 by 2 z inverse plus 1 by 4 z power of minus 2 plus 1 by 8 z power of minus 3. Next, letting h of z to be equal to y of z by x of z, performing the cross multiplication and taking inverse the transform on both sides, we get the equation which is y of n equals x of n plus 1 by 2 x of n minus 1 plus 1 by 4 x of n minus 2 plus 1 by 8 x of n minus 3. And from this we can write the structure, very simple structure. So it comprises of 1, 2, 3 delays are there, and the delays are producing the outputs, that is x of n minus 1, x of n minus 2 and x of n minus 3. These values are scaled respectively with, so x of n is multiplied with 1, so scaling is 1, x of n minus 1 is multiplied with 1 by 2, scaling by 1 by 2. Next we have x of n minus 2 scaled by 1 by 4. Last we have scaling by 1 by 8. Combine all these through addition and the final sum gives you the answer called as y of n. This is called as the direct form 1 realization for the given problem. The next problem is a small variant of this, okay, typically may be asked in the examination. The question goes something like this. Realize the linear phase FIR filter having the following impulse response. H of n equals delta of n minus 1 by 4 delta of n minus 1 plus 1 by 2 delta of n minus 2 plus 1 by 2 delta of n minus 3 minus 1 by 4 delta of n minus 4 plus delta of n minus 5. Now we can easily count and see that the length of this impulse response is 6. We have 6 points. So it is found from n between 0 to 5. Okay. So n here is even. Okay. So except the value at the origin, the remaining points we can see here, they are exhibiting symmetry. Okay. In fact, the entire h of n here is following what is called as symmetry. It is symmetric, correct? So you see first point is same as last point. Okay. So you can see second point is same as last but one. So you look at from the left or the right, we see the same values. Okay. So first we note down what is given. Given is the same. We make a note of it. Then taking z transform on both sides, we get h of z. We know delta of n has a transform which is 1. Delta of n minus 1 is a shifted version of that. Using time shift property, we can call it as 1 into z power of minus 1. So therefore this is the z transform of this, and similarly 1 by 2 z power of minus 2 is the z transform of 1 by 2 delta of n minus 2 plus 1 by 2 z power of minus 3 minus 1 by 4 z power of minus 4. Last term is z power of minus 5. Next, substituting, replacing in place of h of z, we have y of z by x of z. Then after doing the substitution, we can obtain this, and the next step after this substitution is cross multiplying. So we have to cross multiply. X of z is multiplied with each of these terms, okay, and on the other side we have y of z. Then applying the inverse Z transform on both sides, on the LHS we get y of n, on the RHS we have x of n minus 1 by 4 x of n minus 1 plus 1 by 2 x of n minus 2 plus 1 by 2 x of n minus 3 minus 1 by 4 x of n minus 4 plus x of n minus 5. Now here we observe, since the impulse response was symmetric, we observe some of the common coefficients, like x of n and x of n minus 5 has the coefficient 1. Therefore we can collect the terms with the common coefficient. So next, minus 1 by 4 is common for both x of n minus 1 and x of n minus 4. 1 by 2 is common for x of n minus 2 plus x of n minus 3. Therefore, from this we can write the structure. Okay? So how this structure is different compared to direct form 1, it comes from the common terms. So what we observe here, as in the previous case, the number of delays, it depends on the order. So the number of delays we have is 1, 2, 3, 4 and 5. They produce the corresponding outputs for x of n minus 1, x of n minus 2, x of n minus 3, x of n minus 4 and x of n minus 5. Correct? Now we have to see and combine. So x of n is added with x of n minus 5. So you can see the addition here. Similarly, x of n minus 1 is added with x of n minus 4. X of n minus 2 is added with x of n minus 3. Okay? And these sums, they are scaled by the common coefficient. So we have the coefficient for this is 1. The coefficient for this is minus 1 by 4. And the coefficient of this is 1 by 2. Therefore, we take the sum, and after taking the sum, the result here is y of n. So this is called as the FIR linear phase realization. Please note, here we have performed the problem for n is equal to 6. We can have the value which is odd also. So in the case of odd, we will see that all the terms may not be combined. Okay, you may get one element which is not combined in the case of odd, but we have to appropriately scale it and we have to sum it. So this is how the procedure goes if the question is realizing a linear phase realization of FIR. So we can take a look at another numerical belonging to the similar type. Realize the linear phase FIR filter having the following impulse response. The impulse response is given as h of n is delta of n plus 1 by 4 delta of n minus 1 minus 1 by 8 delta of n minus 2 plus 1 by 4 delta of n minus 3 plus delta of n minus 4. So what we notice here again, the length, if you count the points 1, 2, 3, 4, 5. 5 is an odd number. Okay, so whenever you're having an odd number, we can see that the coefficients for delta of n and the last term is common, and 1 by 4 is common for both, but the middle term here cannot be actually combined with anything. That's a small difference. Therefore, in any problem, please note down what is given first. So we copy whatever value of h of n is given. Next, taking the transform on both sides, you know the result now. The answer is 1 plus 1 by 4 z power of minus 1 minus 1 by 8 z power of minus 2 plus 1 by 4 z power of minus 3 plus z power of minus 4. Then h of z is replaced with y of z by x of z, and the value in the RHS is represented as it is. Next step for simplification is cross multiplying and taking inverse Z transform on both sides. We get the difference equation. Y of n is equal to x of n plus 1 by 4 x of n minus 1 minus 1 by 8 x of n minus 2 plus 1 by 4 x of n minus 3 plus x of n minus 4. Again, identify the coefficients which are common. So the terms that are common here is x of n plus x of n minus 4 with the coefficient 1. 1 by 4 is a coefficient for both x of n minus 1 and x of n minus 3, and the middle term cannot be combined. You keep it as it is, minus 1 by 8 x of n minus 2. Next, let us realize the structure for linear phase FIR filter. We again use appropriate number of delays. So since order here is 5, the number of order is 4, the number of delays is 1, 2, 3, 4. Length is 5, the order is equal to 4. Okay, so 4 delays we'll have, producing the corresponding signals x of n minus 1, x of n minus 2, x of n minus 3 and x of n minus 4. Then we collect the terms which are common. So connecting x of n with x of n minus 4. So scaling is done with 1. Next, x of n minus 1 is combined with x of n minus 3. It is scaled by the value 1 by 4. The middle term cannot be combined, so take it as it is and scale it with minus 1 by 8. Add up all and you get the answer as y of n. So you can use either plus symbol or summation symbol to show the addition operation. This is linear phase FIR filter realization. Let us discuss about cascade realization of FIR filter. So given an FIR filter, system function h of z, they are asking you to obtain the cascade realization of h of z equals 1 plus 2 z power of minus 1 minus z power of minus 2 into 1 plus z power of minus 1 minus z power of minus 2. So it is important that you should be able to express the given system function in the form of biquadratic sections. So the meaning of biquadratic sections is that the power of each should not be more than 2. So we can see that each of this term has power which is equal to 2. So if the expression is not already in that form, we can factor it and convert it to that particular form. Okay. So in the solution, you can note down what is given. The given h of z is 1 plus 2z inverse minus z power of minus 2 into 1 plus z inverse minus z power of minus 2. Next, this is expressed as h of z equals h1 of z into h2 of z. This is called as cascading. The value h1 of z is given by y1 of z by x1 of z. So because h of z is y of z by x of z, here we use the term h1, so we use y1 and x1. Now this we can associate with the first term that is given here. Okay. Next, let us cross multiply, take inverse Z transform. Taking IZT on both sides. We get the equation y1 of n equals x1 of n plus 2 times x1 of n minus 1 minus x1 of n minus 2. Now, in a similar fashion, we can obtain similarly h2 of z is y2 of z by x2 of z, which equals the second factor then this can be correspondingly simplified by performing cross multiplication. And then taking the inverse Z transform on both sides, we get the equation as y2 of n equals x2 of n plus x2 of n minus 1 minus x2 of n minus 2. This two equations that we obtained for y1 of n and y2 of n can now be used to realize the structure. Therefore, first we consider the input, which is called as x of n. On the other end, we'll get the output called as y of n. So the first implementation will be that of the equation that we obtained first. There, the relationship we saw was the input x of n. Okay, since input x of n for the first stage is called as x1 of n, right? It's called as x1 of n. We can write the structure for that in direct form. In direct form, we can write the structure for that as follows. So this will be the direct form realization. The scaling here we know is performed when you inspect the equation. First we had what is called as, this is x1 of n as it is, no scaling. Then we have what is x1 of n minus 1. Then we have x1 of n minus 2, which is appropriately scaled with the value. So here no scaling, so therefore it is 1. Next here we are scaling it with 2, and last term is scaled with minus 1. So these are the appropriate scales, and then we come to the second stage. So we write the second stage now. The second stage is implemented in a similar fashion. So again, the number of delays we have is equal to 2 because the power is 2. We perform the addition of the respective outputs. Okay, so let us assume that the input here is called as x2 of n. So we have x2 of n here taken. Then here we get x2 of n minus 1. Here we have x2 of n minus 2. Okay, and the second equation, difference equation shown here, tells us about the scaling. So x2 of n, no scaling or scaling by 1. Second one is also scaled by 1. Third one is scaled with minus 1. So this input produces the corresponding output. So y2 of n should be same as the final output. So this sort of arrangement where each of the sections were implemented separately. So this part, let us call it as the first stage. So this is what is called as stage 1. this corresponds to the system function h1 of z. Similarly, this block here, the portion here, can be called as stage number 2. So stage 2, we can have what is called as h2 of z. Okay, so this sort of arrangement is called as cascade, where we have the blocks placed one after the other in series.
Thank you all.